and I'm going to start the video on our piece of paper. Get that sorted out. Do you have some questions lined up?
I had a question about the homework,
Okay.
section 4.5, part 2.
All right. 4.5 in WebAssign.
Yes.
Was there a particular problem?
Yes, I had two questions, one for the fourth problem.
Okay, great. Let me just grab that. I'm just navigating to the WebAssign. I want to put it in student preview so that I don't give away the farm. 4.5, part 2.
Yeah.
Okay. In standard factored form. Problem number 4, did you say?
Yes.
All right. Thanks for your patience. Let's get this screen share up so that we can look at this together. Problem 4. Do you want to? Oh, that's the one about standard factored form of a perfect cube.
Yes, I understood the first part, A, where we find the formula,
The
or
standard
just the,
factored form. Uh-huh.
yeah, but maybe I missed this in the book, but for the least positive integer k.
Uh-huh. All right. So I'm going to write down a couple of things. This is our WebAssign 4.5 part 2 and standard factored form, problem number 4. And it's worth going ahead and looking at uh, part A as well. I'm going to stop sharing and you're going to read to me part B in a minute, right?
Yep.
Okay, perfect. Thank you. I think we need a little focus adjustment here. How's that? A little bit better? So the point is, if A is an integer greater than or equal to 2, I think in the notes we called it n, but the point is we can write it as prime 1 raised to exponent 1 times prime 2 raised to exponent 2 dot 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 prime, say, k raised to exponent k. Do you agree? Now,
Yes.
so let's just think about something that we're really familiar with. Uh, for a perfect square, because we've talked about perfect squares at some length, let's say n is equal to a squared, okay? So n is equal to all of this good stuff, and I can talk about this and not give away the farm on that part A, because if I talk about perfect squares, then hopefully people can translate this idea to perfect cubes. But the 2 gets distributed, right, by laws of exponents. It's P1 raised to the E1 squared times P2 raised to the E2 squared. And you might not, have done all of those steps, but I'm going to show them. That's a law of logarithms, right? And that's the law that says if we have xy to the n, we can distribute that exponent n across the factors. And that's what we're doing here with, maybe I should call it something else. Maybe I should call it e for exponent to the e. And we can distribute that exponent across the factors. Well, of course, then there's a law of logarithms, or excuse me, exponents. Of course, logarithms and exponents are inverses of each other. That says if you've got x raised to the e quantity raised to the g, you can just multiply those exponents. When we raise an exponent to an exponent, we multiply them. So it's p1 to the 2e1 times p2 to the 2e2 all the way out to p sub k to the 2e sub k. Now, what do you notice about each exponent in the standard factored form of a perfect square?
It moves from lower to higher?
Oh yeah, the primes sure do. We always write the primes in ascending order, but that's true whether or not the integer n is a perfect square or not. Do you agree?
Yeah.
So what do you notice about each exponent in the standard factored form of a perfect square? Which is what we are looking at when we're looking at this n right here. This is a perfect square, right? What
They're
happened?
all, oh, I'm
Yeah,
sorry.
yeah, go ahead. Sorry.
They're all times two. I don't know what else.
Yes, yes, they are all even. They all have a factor of 2. They're all even, right? So if we look at a perfect cube, where n equals a cubed, right, instead of a perfect square, and we look at, n is equal to, I'm not going to go through all of those steps, but I'll at least write the first part where we're substituting in for a, because it's got this nice standard factored form. What do you think is going to be true of all of the exponents when n is equal to a cubed? In other words, when n is a perfect cube.
They'll all be multiplied by three.
Yeah, they'll all be multiples of 3. Yes, they all have a factor of 3. It's a fine point. So, and there is something called a perfect quartic, and that's an n that looks like a to the fourth. There is something called a perfect quintic. That's when n equals a to the fifth. And this same idea generalizes, right? What do you think every exponent is divisible by if we're looking at n, which is a perfect quartic? It's equal to a to the fourth.
They would all be multiples of four.
That's exactly right. So the next game, and I really like this game, and you're going to read it to me. It says, find the least positive integer k that makes, now can you read to me all the factors?
2 to the fourth
Uh-huh,
times 3 to the fifth
uh-huh,
times 7
uh-huh,
times 11 squared
times k, right?
times k.
That makes this, and of course, what is the exponent on the 7, even though we don't write it?
1.
Great. So this is our n, okay? And we want to make this expression a perfect cube. Well, what we're hoping folks realize is that that means all of the exponents, when this is written in standard factored form, have to have a factor of 3. So we get to build k to correct these exponents just to make them just big enough so that they will all be divisible by 3. So that's our strategy. Build k, build the integer k to make each exponent in 2 to the fourth times 3 to the fifth times 7 times 11 squared times k a multiple of 3. So let's try to build k. All right. Does this make sense?
It does.
Yeah, it's a fun game.
If I could
Sounds
just jump in real quick,
yes, please.
it's because n equals those exponential fact elements, I guess, the elements to
It's
with
the
their exponent.
product. Yes, n is the product of all of these And you're right, these are exponentiated factors.
And
That process is called exponentiation. Go ahead.
because n is not raised, well, n is raised to 1, but it's not raised to something larger than 1. So those exponents are multiplied by 1, so they don't appear to change. I think I'm getting ahead of myself.
Well, we want n to equal a cubed for some integer k, right?
Right.
So let's look at each factor and see what we need to add until that factor has an exponent that's divisible by 3.
Didn't we just multiply all of the exponents by 3?
We could, but that would build much larger than the least positive
Oh,
correction. So the game is we're going to add some factors, but the game is to add the smallest number of factors to build the smallest k that will make n a perfect cube. So let's look at each prime and its exponent. See the game? Yeah, but you're right. Yeah, if we just said, okay, we're going to make k equal to whatever the other factor is that would make all of this cubed. That's huge. And so let's look at 2 to the 4th. Okay, so 4 is not divisible by 3. So we're going to do a correction. Okay, as we build k. So what is the next smallest integer that is divisible by 3?
6.
That's right. So we want 2 to the 6th. So in our correction, we're going to include how many copies of 2 is the increase from 2 to the 4th to get to 2 to the 6th?
1/2.
Well, how many copies of 2? How many copies? What do we have to multiply 2 to the 4th by to get 2 to the 6th? Okay,
All
so
I can think of is a fraction.
no. Let's well,
Oh,
remember we got to review the laws of exponents, right?
I forgot. I'm sorry.
No, don't be sorry. X to the n times x to the m is equal to x to the n plus m, right?
Oh,
That's an exponent law, just like these other ones were exponent laws. So we need to include 2 squared in our k because that will correct the 2 to the 4th factor. If we make 2 squared a factor of k, then we'll be able to collect together the 2 to the 4th times the 2 squared that'll be over here in k, and the grand total will be 2 to the 6th. And that fixes the factor that's got the base 2. Okay, so P1 equals 2 is the first one we did. All right, let's look at the next prime factor. P2, what is the second prime factor in this n?
3 to the 5th.
Okay, so we're looking at the prime 3, and yeah, we're going to correct 3 to the 5th. Well, what do we need to do to correct? What do we want?
3 to the 6th.
Exactly. So the correction is to include what factor as we build k?
3 to the 1st.
That's right. All right, let's deal with the next prime factor of n. I went ahead and named it n just because it's easier to talk about it if it's got a name, right? But all the exponents have to have a factor of 3. So P3 is 7. So we've got 7 raised to the 1, right? What do we want?
7 to the third?
We do. We want 7 because 3 is the smallest integer. You know, if we're counting up from 1, it's the next integer that's divisible by 3. So what will we include as we build k?
7 squared.
That's right. We need 7 squared, right? Because 7 to the 1 times 7 squared will get us the 7 cubed. And here, of course, 3 to the 5th times 3 to the 1 to be consistent and write all the pertinent information is our 3 to the 6. What's the last prime?
The last prime is 11 squared.
Okay. So P4, oops, we got 4 different primes. So we got all the way up to P4. So we've got 11 squared. So what do we want?
11 cubed?
Yeah,
11 to the 3?
yeah. 11 cubed or 11 to the 3. Because, right, 11 squared times, oh yeah, so what do we need to add? What do we need to include? How many?
11.
Yes, times 11 will be our 11 cubed. So we know what we need to do and that's 11 to the 1, just like it was 3 to the 1. So now we know what to do to build the smallest positive integer k that's going to make this a perfect cube, right? Let's build k. So k is going to equal 2 squared times 3 to the 1 times 7 squared times 11 to the 1. And now let's check it. So our n is 2 to the 4th times 3 to the 5th times 7 to the 1 times 11 squared times k. But our k is this. So let's put it in there and see if it really worked out. And this also kind of reinforces these laws of exponents that some folks might be a little rusty about. So it's 2 squared times 3 to the 1 times 7 squared times 11 to the 1, right? And now we can just rearrange these factors and put the 2 to the 4th next to the 2 squared and the 3 to the 5th next to the 3 to the 1. You get what's going on here, right? And
Yeah.
I'm going to give you a do later because I feel like I've spoiled it for you. And that really is 2 to the 6th, which is divisible by 3, times 3 also to the 6th. What's 7 going to be raised to?
7 to the third?
And what about the 11?
11 to the third.
Okay, and can we write that? You know, we're going to check. Is n a perfect cube, right? That's what we want. Well, it is if we can write it as a cubed for some integer a. So if we factor out a 3 from each of those factors, what's left in here? What's our a?
2 to the, 2 to the third.
Let's see. When we raise an exponent to another exponent, we have to multiply.
Oh,
Remember, x to the n raised to the m is x to the n m. So when we multiply whatever this exponent is here times 3, we have to get 6.
so 2 to the second.
That's right. 2 to the second times 3
3 squared.
to the second times 7 to the what?
First?
Uh-huh. Times 11 to the what?
First.
That's right. And that is equal to a cubed for a equals 2 squared times 3 squared times 7 times 11. But this is our K that made that happen.
Oh,
All right, so shall I give you a do later?
yes, please.
We're going to let n equal 2 to the 4th times 3 to the 7th times 5 to the 1 times 7 to the 5th times 11 to the 7. Oh, we already got a 7. Let's say 11 squared. Two parts. Find, oh, times K, okay? Let's put the K in there. It's easy to miss the K. Find the smallest positive integer K No, I think I picked up the other, not the black one. Find the smallest positive integer K that makes n, in fact, I don't even need an A. I'll just do two parts. That makes n a 1 perfect square, and then 2 a perfect cube. So that's two little problems. But if you understand what was going on, you'll be able to do it. And some
Oh,
of them don't even need to be corrected. In fact, maybe we should make, let's do this. Let's make 11 cubed. That way you have one that doesn't need to be corrected, right? When you're building a perfect square, and you'll have one of these that doesn't need to be corrected when you're building a perfect cube because they're already going to be okay. Does that make sense?
yeah, thank you.
Mm-hmm. It's a fun game though, isn't it?
Yeah,
I
I
was
was
hoping
right.
somebody would ask me about it. Yeah, yeah, that's one that is a really good review of laws of exponents. Have you ever thought about why the laws of exponents are the way they are? Maybe sometime when we're not real busy, I can show you why the laws of exponents work the way that they do, or you can even check for yourself why they actually work.
That would be cool.
I'd be happy to. All right, Darius and Tega, great to see you. Darius, you were in the room a little bit earlier. Um, would you like to ask a question? Okay, Tega, do you have a question? It's good you're here. Hello, maybe you're muted.
Yeah, I was muted, sorry. Hmm, Could
Can you
we
speak up, please?
uh, could we go to um the homework section 4.5?
Sure. Part one or part two?
Part two.
Part two. Okay, so which number would you like to look at?
I would like to go to number one because so far I know that I like have like issues with things whenever I do the homework.
Tega, I'm so sorry, but really, I'm so sorry. It might just be me, but I just can't hear you. Can you speak up?
Sorry. I said I would like to go do the number one because whenever I do the assignment, I always like have a struggle with it.
Okay, well, why don't we try writing the proof and then you can go back and try to see what steps are appear in what order. Does that make sense? I really can't hear you. I don't know what's going on. Maybe you can get closer to your speaker, but I understand that you're wanting to look at WebAssign 4.5 part 2 number 1. But I just can't hear you. Okay. So rather than actually answer the question, this is an interesting problem. It's a proof by cases. And it turns out, if we review the extra steps that we need to go through when we're writing a proof by cases, an interesting thing happens with this particular one. Of course, when we have a statement that's not written in if-then form, the first thing we try to do is write it as an if-then. Do you agree?
Yeah.
Oh, now I can hear you. What happened?
Sorry, my mouth is kind of swollen, so it's like,
Oh, but it's like a whole different world now. This is great. The square of any integer can be written. Did you have dental work or something? I hope you're okay. And one,
not yet. I hope so.
oh goodness, I know what you mean. And one of the two forms, 4k or 4k plus 1 for some integer k. Am I still sharing?
Yes, you are.
Am I sharing the screen? Oh, okay, fine. You're seeing this. Okay, great. So let's go ahead and write it in if-then form so we can identify the hypothesis and the conclusion. And we wrote several proofs. This is the hardest part, but I'll give you a big hint. In these proofs by cases where we're obviously using the quotient remainder theorem, the hypothesis is always going to simply be that we have some integer. Even though the statement's about the square of an integer, we might write if x is the square of an integer, then it can be written into one of these two forms. But it's actually much easier just to say if n is an integer, we always want to just have an integer as our hypothesis. Then we can talk about n squared because the square of an integer looks like n squared. And this will look a lot like a problem that we did. It says either n squared equals 4k or n squared equals 4k plus 1 for some integer k. So you can compare this statement to some of the statements that we did work in class. And what we have is the hypothesis that n is an integer, and then we have a compound conclusion. And we're just going to assume that we have an integer n, and then we want to prove that either this happens or this happens. Now, for proof by cases, we have two other steps that we execute in order to also identify the divisor and set up our cases. So step one is look at the conclusion. To identify the divisor D. And then step two, what we have seen so far, and that's what makes this one interesting, is use D to set up cases with the Q-R theorem. However, we're going to amend that now with a little bit more information, which is what's displayed here. And that extra information is that if D is a power of a prime, then we might be able to set up fewer than D cases. We might be able to just set up the prime factor number of cases. All right, now. All right, first of all, let's just look at the conclusion. Do you remember what the Q-R theorem says? It says A equals D times Q plus R. And in fact, we could list the possible remainders. The remainder is either 0, 1, ... up to D minus 1. That's another way of saying 0 is less than or equal to R is less than D. These are our possible remainders. The remainder could be 0, could be 1, could be all the way up to D minus 1, but the remainder cannot be as large as the divisor D. Do you remember that?
Yeah.
So when we look, let's execute step 1. When we look at the conclusion, thinking about the quotient remainder theorem, what is the D that's being used in this conclusion? D sits right there. So and they're not calling it Q, it's okay, they're calling it K instead of Q, but K is still the quotient here and here. What is the D?
The N equals 4K.
Yeah, so what is the actual value of D? Do you see the D sitting here?
4.
Yeah, it's 4. So D is 4. But the amendment is this. From what we've learned, we would set up 4 cases. We would apply 4 cases to the integer in the hypothesis. Apply the D cases to the integer in the hypothesis, right? This is our hypothesis. This is our conclusion. But it turns out the amendment is, am I spelling amend correctly? Or does it have 2 M's? I think it's one. If D is some prime raised to some exponent, we might be able to use P cases. So this is new. And because they're just asking you to rearrange the statements for that proof, and they set up the cases for you, notice we're going to use the amendment. Four is actually equal to the prime 2 squared. So the prime is 2. We can actually use 2 cases because the divisor is a power of 2 and it doesn't have any other factors. It turns out you can often just kill the proof, so to speak. We say kill the proof in P cases. In this case, 2 cases. We can use P equals 2 cases. And you might not have even noticed that, but maybe you did when you started to try to figure out this proof. So let's write the proof. We're going to let n be an integer. What do we wish to show? Well, we wish to show something about n squared, that either n squared equals 4k or n squared equals 4k plus 1, where k is in z. we must prove this. I'll just write this in our thinking notes. We must prove this in each case. No matter how many cases we have to prove the wish in every case. Are you with me?
Yes.
Great. Now, they tell us we're going to use D equals 2. So using D equals 2, the Q-R theorem says, okay, so we apply D cases to the integer in the hypothesis. That's why we always know we want to have an integer in the hypothesis. So if we're dividing n by 2, the Q-R theorem says, hey, you can do that, guaranteed, and you will either get a remainder of 0, which means n is actually even, or you'll get a remainder of 1, because it could be that n is odd. We don't know. That's kind of the point. All we know about n is that it's an integer. We don't know if it's divisible by 2 or if it leaves a remainder of 1 when we divide it by 2, but we know for sure one or the other of those happens. So this is our, our important statement that we write, setting up the cases, to let the reader know, what are we doing? The Q-R theorem says n equals 2q, or n equals 2q plus 1, where q is an integer. And now we know that we have 2 cases to write, and in each case, we're trying to satisfy an or statement. This is an or statement, and we can show that or statement is true if we show that either component is true. Does that make sense? This is called a component. That's our or, and this is called a component. The or statement is true if we show either this or that. And you know what? In one of the cases, we're going to get that n squared looks like 4k. In the other case, we're actually going to get that n squared looks like 4k plus 1. Shall we do it? Shall we work it through? Let's write the proof. Yeah. So let's start on case 1. And see, our nice kind of setup here tells us, oh, okay, I know exactly what to assume or suppose in case 1. We're going to suppose n equals 2q. The wish is the same. We wish to show n squared equals 4k, or n squared equals 4k plus 1. Okay? One or the other. This is an or, right? All right, well, let's look at n squared. So, notice we're n squared. What is n squared?
N squared equals 2q.
Quantity squared. And what does that turn out to be when we multiply that out?
4q.
Squared, right? Because when we multiply 2q times 2q, right, it's 2 times 2 times q times q, right? So it's 4q squared. Ooh, look at that. Our k can be the q squared, can't it? Since q is in z, k equals q squared is in z, right? Since this q is an integer, if we set k equal to q squared, that's an integer. I don't really like having that there. I'm going to go ahead and put it on the next line. Since q is in z, we see that k equals q squared is in z, because what operations are we using to build k from q?
2.
Multiplication, right? We're multiplying Q times Q. So because products of integers are integers, Q is an integer, and we're building K by multiplying Q times Q. So we know K is an integer because products of integers are integers. And so what we've done now is we've proven that n squared, which is what we wanted to say something smart about, right, is equal to 4K, where K is in Z. So in this case, n squared winds up looking like 4 times an integer K. And that means that the OR statement, n squared equals 4K, or n squared equals 4K plus 1, with K in Z, is true. That statement is true because we proved that this component was true. Are you with me?
Yeah.
So we finished case 1, and we're able, even though D is 4, we're able to write this proof in 2 cases, because sort of the magical thing about the Q-R theorem is that if your divisor is like a power of 2, like 4 or 8 or even 16, you don't necessarily have to write 4 or 8 or 16 cases. All of those numbers only have 2 as a prime factor. Sometimes you can write the proof in just 2 cases. Now, if you have a divisor like 25, we know that we can always work it in 25 cases, but nobody wants to write 25 cases. What do you think we might be able to use in terms of how many cases do you think we might be able to get away with if D was 25?
5.
Exactly. Right. And if D was 9, we might be able to do it in fewer than 9 cases. How many cases might we be able to use?
3.
Exactly. And this is the magic when the divisor is a power of a single prime. I'll tell you right now, if D is 6, which is 2 times 3, we won't be able to write it in 2 cases, and we won't be able to write it in 3 cases. We'll have to use 6 cases. But sometimes magic happens and that's when the divisor is a power of a single prime, like 2, or, So what's case 2 going to be? See, it's nice that we wrote out in our proof, we said, oh, we have to use the Q-R theorem. We're going to try D equals 2. What's going to be our suppose statement for case 2?
Now,
See what we used for case 1?
n equals 2q plus 1.
Exactly. Very good. And that's why it's so nice to write out what the cases are going to be at the very beginning, because then you can just say, you know what, I don't have to worry about it. I've got them written down. I can go back and look, and I'll make sure I don't miss any cases. It's the same wish, okay? We still wish to show something about n squared, that it's either going to look like 4K or that n squared looks like 4K plus 1, okay? Same wish. All right, so we want to say something smart about n squared. Let's look at n squared. What is n squared going to look like? We're going to put in 2q plus 1, of course. And what is 2q plus 1 quantity squared? Can you do that one in your head?
That's 4q plus 2.
4. Okay, let me show you how to do that. 2q plus 1 times 2q plus 1. Are you with me?
Yeah.
All right, so if we want to multiply these, there's this thing called FOIL. where we take, all right, FOIL stands for the first, the outer, the inner, and the last. All right, what am I talking about? All right, so when we look at these two binomials, the first term in this binomial is 2q. The first term in this binomial is 2q. So we're going to have to multiply together the first times the first. So what is 2q times 2q?
That's 4.
4. And then what happens with the q times the q? How do we write that?
Q squared.
Perfect. Now we're going to do the outers. Okay, so see how this is sort of spread out? We call the 2q on the left and the 1 on the right the outer terms. This is the way it goes. Firsts, outers, inners, because these are on the inside, and then the lasts. So we multiply the first together. We're going to multiply the outers together. We're going to multiply the inners together. Then we're going to multiply the last terms together, and that way we won't miss any terms. So what is the product of the outers? What is 2q times 1?
2.
Yeah, it's just 2q. Now let's multiply the
2Q,
inner.
okay.
See it?
And 2Q and 1 times 1.
Okay, so if we gather the two q's together, this is 4q
Q
squared.
squared plus 4Q squared.
Now these are just q's to the 1. That's why
Okay.
they go together, right?
Yeah, plus 1.
Perfect. Nice. So we'll write it here. It's 4q squared plus 4q plus 1. Good job at that, actually. Now, whew. All right, so this is what n squared looks like. You know, at this stage of the game, I might even be lost. I may have even forgotten, what am I trying to do? That's why I write the wish. We write this wish and we don't have to worry about forgetting what we're trying to do. We can just go back and look at our wish and remember, oh yeah, we're trying to prove either n squared equals 4k or n squared equals 4k plus 1. Which of these two do you think this n squared is going to wind up looking like? Is it going to look like 4k or is it going to look like 4k plus 1?
Okay, plus 1.
Yeah, exactly, because we can factor out a 4 from these two terms, and this plus 1 will still be hanging off the end, which is perfect. So let's go ahead. I don't need a period there. We can just keep on working. Let's factor out the 4. What's left when we factor a 4 out of the terms that we can do?
So
Q squared.
the Q squared plus 4Q.
Well, we're going to pull the 4 out front. So what's left here?
Q
Yes.
plus 1.
Yeah, and then 4 can't be factored out of 1, so that's there. And this now is going to be our k. So all we have to do is talk about why k is an integer. Well, it's built from q. Since q is in z, and what operations are being used to build k here from q? Q squared plus q. What operations are we using?
Q.
Well, what are we doing when we're taking a q squared? What's the operation that's really happening? Like, is it addition? Is it subtraction? Is it multiplication? This is really q times q, right? So this expression, q squared plus q, is constructed by using multiplication and addition over the integers. So since q is in z, this quantity k, we're calling this k now, equals q squared plus q is in z because, I'll say it a different way than I said, because z is closed under multiplication and addition. Or you can say products and sums of integers or integers. You can say it either way. I think that in the ebook, they use this second way. But however way you say it, we've just showed that n squared equals 4 times k plus 1, where k is an integer. So we have proved, or we have proven, either way is actually correct, n squared equals 4k, or I'll put it in quotes, n squared equals 4k plus 1 for k in z holds or is true. So we've just gotten our wish in both cases. And that means that it's true no matter what n is. So you'll have these notes, and this would be what a real proof, if you wrote the proof out, what it would look like. And I think if you go through these, yes, they shorten things up in this problem. Okay, they shorten it up. But if we take a peek, can you see it okay?
Yeah, I can.
Notice how, I'm so sorry you have a toothache. I'm so sorry. Notice how they use d equals 2 and they set up two cases, right, for some
Yeah.
integer q. So there are two cases, and here you just need to try to, it turns out you're going to be able to pick 5 of these. You can pick 5 of those statements in order, right? So the assumption that n equals 2q is already included in the proof. You don't have to write that. So if you were looking at our proof, the suppose n equals 2q, well, they've already given us this part where q is an integer. But the next thing is to try to figure out what's the next thing that happens, right? Right. Well, the next thing we did was we were looking at n squared. So probably the next step is going to be either this one or this one or this one. One of these is going to be your first statement, right? Oh, no, to prove case 1. Okay. All right. We do have to pick the hypothesis. We do have to say that n is equal to 2q. Okay. So I was wrong about that. I'm glad I looked. So yeah, they want us to give the correct hypothesis for the case. That's good. I'm glad they did. Now, which of these will be right? Is n squared equal to the first or the second one or the third one or the fourth one? You can go back and look at our algebra because we did this work, right? We did that work.
Yeah.
And then you can look through what we were trying to prove. We were trying to prove that n squared looks like 4 times k. Well, our k looked like q squared, right? And then we talked about why k was an integer. Okay, so you can probably refer to this proof and think it through, and you'll be able to pick the right answers. And if if you need an extension on on it, well, you still got till tomorrow, don't you? So you should be okay.
Yeah.
Darius, are you back with us? I tried to get you to ask a question a while back, but you were not quite in earshot. Do you have a question, Darius?
Yes.
Hi.
I was just trying to do the assignment for 4.5, I think question 2.
Uh-huh. And you were having some issues with question 2. Let's take a look at it, shall we? I'm going to share my screen again. All right, question 2. You want to read it to us?
Yeah, sure, I can do that. Say use the quotient reminder theorem with divisor equal to 3 to prove that the square of any integer has the form 3k or 3k plus 1 for some integer k. And say proof n, suppose n is any integer by the quotient reminder theorem with d equals 3. We know that n equals 3q or n equals 3q plus 1 or n equals 3q for some integer
Yeah.
q. We must show
So
that.
what is the right number here? What are the possible remainders if we're dividing by d equals 3?
But I put 1 in there.
Well, we've already got one though. You see, the first statement, n equals 3q, what's the remainder? If n turns out to look like 3q, what was the remainder there? 0. It means that there was no non-trivial remainder. Let's talk about this. Remainders and the Q-R theorem. Okay, so A is an integer, D is NZ plus, A, there exists, this is unique, a unique Q and R and Z such that, so we suppose we have an integer A and a positive integer D. This means there exists unique Q and R and Z, or integers Q and R, such that A equals DQ plus R, where there's an inequality. Do you know what the inequality says? Do you know the Q? Did you break out the book and look at the notes at what the quotient remainder theorem does say, Darius?
I just forgotten about it. I was just reading about it a couple
Well,
of minutes ago.
well, hang on. Hang on. Let's go take a peek. You've forgotten about it. So that's okay, of course. I mean, we don't remember everything. Of course we don't. So let's go to our resources, okay? Let's go to the class notes. Shall we do? We started talking about the quotient remainder theorem in section 4.5. So let's take a look at the class notes because I try to write almost everything. Once in a while, I'll leave you kind of on your own to work through a problem, but I really do try to give you everything that's really important. So here's the information, the quotient remainder theorem, and this is the inequality. And it tells us that when we're dividing by D, we don't want the remainder to be too big. Like if we're dividing by D equals 9, for example, we don't want to get a remainder of 9 or 10, right? If you're dividing by 9 and you get a remainder of 9, you would go back in there and pull out another copy of 9 out of A, right? Your quotient would be 1 larger, remember?
Yes.
So if you go, so I encourage you to make use of these resources that we have, right? So let's talk about this inequality where 0 is less than or equal to R is less than D. This is really important. It says when we divide A, we're dividing A by D. D is the divisor. That we will get a remainder that isn't too big and it can never be negative. And we went through a bunch of examples and talked about it. Were you in class the day that we had that lecture?
Yes.
Good. So maybe if you read over the notes, you'll remember how we carefully went through a bunch of examples I would give the A and the D, and then your job was to find the Q and the R, and we discussed it at some length. So this is the deal. If D is 2, what are the possible remainders? So if we're dividing an integer by 2, what are the possible remainders that we might get?
0 and 1.
Yes. So if D equals 3, what are the possible remainders?
0, 1, and 2.
Exactly. So let's just look at that. If we know that A equals is an integer, okay? And we apply the Q-R theorem with D equals 3. That means there are 3 different possibilities. We don't know what A is. We just know it's an integer. We know we can divide it by 3, and it's either going to look like 3 times Q, or that means the remainder is what? If A equals 3 times Q.
Remainder could either be 2, 1, or 0.
Yeah, but in this particular case, if A actually is 3 times an integer Q, what is the remainder for that particular A right there? The remainder is actually, that's the case when the remainder is 0, because A is a multiple of 3, right? Or A could equal 3Q plus 1. Or A could equal 3Q plus 2, right? A will look like 3Q plus 1 in the case that the remainder is 1. A will look like 3Q plus 2 in the case that the remainder is 2. Here, Q is an integer in all of these, okay? And so we use this information to set up our cases. And it gives us a quantity to substitute in for A. A is either going to look like 3Q, or A is going to look like 3Q plus 1, or A is going to look like 3Q plus 2. You see where I'm going with that?
Yes.
All right, well, let's go back now and look at this problem. So in this particular problem, D is 3. So we're setting up the cases. If you go back and look at the class notes, there are going to be little stars where we set up the cases using the Q-R theorem at the beginning of every proof by cases. We use the Q-R theorem. So if D is 3 and our integer isn't A, it's called N, but that doesn't really matter, does it? So you help me now. Either N equals 3Q, or N equals 3Q plus 1, or what would we put here for the other possible case?
0.
Okay, let's go back and look again. A is either, just call it N if you need to. A is either equal to 3 times Q, or A is equal to 3Q plus 1, or A is equal to 3Q plus 2. Because you told me the possible remainders when we're dividing by 3 are either 0, 1, or 2. This is the case where R is 0. Do you see it? Because we don't write
Yes.
plus 0, but it's actually there. This is the case when R is 1. It's 3 because D is 3, Q is our quotient, plus R. R is 1 in this case, the second case. But in the case when the remainder is the largest it could possibly be, which is 2, A or N looks like 3q plus 2. Do you see that? So
Yes.
let's go back now and try again. So this is the case when r is 0. Do you see that? If n equals 3q, that's really the case when the remainder is 0. This is the case. This is what n looks like if when you divide it by 3, you get a remainder of 1. N looks like 3q plus 1. Or what's the other case? N
2,
equals 3q plus.
2.
Exactly. Good job. Do you understand it now?
Yes.
Okay, so that's how we set the cases up. Very good. So once you understand that, that's like huge, because now you understand what the hypothesis is going to be for the different cases. We have 3 cases we're going to argue. In every case, this is key. In every case, we have the same wish. We wish to show the square of the integer, we're calling it n, so we want to show the square of n has either the form 3k or 3k plus 1. Now, what just happened, I think, was you were experiencing one of the most common misconceptions that students have. You were looking at the conclusion, and in the conclusion, it's talking about the square of the integer, either looking like 3k or 3k plus 1, right? So you were thinking that we would only have cases where the integer n would look like 3k or 3k plus 1, weren't you? And you were trying to figure out what could possibly go here. Is it 0 or is it 1? No. We still have 3 cases because we don't know what the remainder is when we divide n by 3. What we are going to prove is that when we divide n squared by 3, we cannot get a remainder of 2. We're going to show the remainder always looks like 0 if n squared is 3k, or the remainder looks like 1. That's the case when n squared equals 3k plus 1. Now, if you go back and look at the class notes from our last class, and let me see if I can find those. Okay, so this was day 12. If we go back and look at day 13, you see I knew that I had assigned this problem in WebAssign. I promised you organized lectures. I've been doing this a long time. So if you look at example 2, it is exactly this problem that we're looking at in WebAssign. Consider this claim. When a perfect square is divided by 3, the only possible remainders are 0 and 1. And when we write it as an if-then, and if n is an integer, then n squared equals 3k, or n squared equals 3k plus 1, where k is in z. That is the same claim, just written as an if-then. So you might want to review these notes, okay? I left case 1 for you to do because I figure the algebra when n equals 3q, which is case 1, is pretty easy. N squared is going to look like 3 times an integer k. And you can look at the earlier notes from tonight, okay? Because or maybe you were even here in the room. We actually worked through case 2 together in class. Case 2 is when the remainder is 1 when you divide n by 3. We still have the same wish. We either want to show n squared equals 3k or n squared equals 3k plus 1. So we went through the algebra, we factored a 3 out of the first 2 terms, and lo and behold, n squared winds up looking like 3k plus 1, which means the statement that n squared equals 3k or n squared equals 3k plus 1 is true. And I've left case 3 for you to do. I recommend that you actually push a pencil or pen, whatever your preference is, and write out cases 1 and 3 yourself for the practice so that when you go back into the WebAssign, you're going to be able to fill these blanks in with ease. Now, I said, oh, did I assign this where you have to, okay, well, you can upload a file here with this. And honestly, if you want, you could just say, see my proof portfolio. Wait a minute, this is one of the ones in the proof portfolio, isn't it? No, it's not yet. It will be. So you don't have to worry about uploading a file, but if you choose to upload a file, then just write it and make a PDF. I've already explained how to do that with the proof portfolios. Just make a little PDF or a JPEG, and then just, use your phone, just take a picture of it, and you can upload case 3. And that way I can take a look at it. Okay?
Okay.
Did you understand part B? Nura, I think you also were asking about, was it this problem you were asking about?
It wasn't this one. It was mod. The last
The
office
last
hour
one.
you had, I asked you about mod.
Yes. And the point is, we're saying that when we divide n squared by 3, we can only get a remainder of 0 or 1. Well, that exactly means that given any integer n, either n squared mod 3 is 0, because mod is the remainder, or n squared mod 3 is blank. Or equivalently, n squared mod 3 is not equal to blank. Okay, so you
I
should
ask
go
just
ahead.
really quickly.
Mm-hmm.
I did case 3. I wrote it out, and I must have done something wrong.
When you
Uh,
tried to upload the file,
no, no. In the algebra that I did, the answer that I got. Do you mind if I tell you what I got?
for case 3,
Yeah,
you should get 3k plus 1. Is that what you got?
I got 3k plus 2.
Oh, let's take a look at it. Let's take a look. That's frustrating, isn't it? So n is equal to 3q plus 2,
Yeah.
and we wish to show that n squared either equals 3k or n squared equals 3k plus 1, where k is in z, right? Oh, and let's say q is in z too. All right, well, let's take a look. What is n squared? Let's do it. Let's write it out. It's 3q plus 2 quantity squared, but we can go ahead and just write 3q plus 2 times 3q plus 2, right? And let's use our FOIL. Firsts, outers, inners, last. When we multiply. So when we multiply the first terms, like this is the first term here and this is the first term here, what is 3q times 3q?
9q?
Well, it's 9q.
Q squared, I'm sorry.
Yeah, don't forget your q squared. Good. The outers,
6q
and it's a plus. Good.
plus 6q
Uh-huh.
plus 4.
Great. Well, remember, if you look at the notes, when you have a number hanging off the end that you can't factor a 3 out of, we apply the Q-R theorem to A equals 4 using the same D that we're dealing with. So if we rewrote 4, so remember how we did it? 4 equals 3 times something plus something. What is the quotient when we divide?
1.
And
4
what's the
equals 3 times 1 plus 1.
Yes. So the remainder is 1. This is 9q squared plus 12q plus 3 times 1 plus 1. And now each of these has a factor of 3 in it, right? And then there's a plus 1 hanging off the end.
Oh, I got 3q squared plus 4q plus 1, but I added those ones together.
Yeah, but this parentheses is supposed to keep them apart.
Oh.
So did you read my email? I tried to look at every single problem of your docx file. I wasn't able to write on it, but did you get my email?
I got the first one you sent. I didn't get this one. I'll check now.
What? I sent it this morning because
Oh,
I wanted you to have a chance to look at it. Um, but anyway, I commented on every single problem and I noticed that you convinced yourself that a false statement was true because
oh no.
you managed to factor 2 out of 3
Oh
because
no.
you thought you were trying to prove something was even. But it
Oh no.
wasn't. But we do that. Mathematicians do that. Like we'll make an error to kind of make something happen that we think is what we want to have happen. Anyway, other questions? You can look at that later, Nura. It's still going to be there. Did that help, Darius?
Yes.
So listen, what are the steps to success? Read the class notes. Goodness, definitely review. And in fact, I would recommend that you actually write the notes during class. Because what's happening is you're sitting in class for 75 minutes, you're watching me do stuff, but you're not. Are you writing notes, Darius? Or do you just know that they're going to be posted so you don't write notes? It's okay.
I do write them after you post them.
You write them up after I post them?
Yes.
That's good. You might try to make some few notes during class too, because there's something called muscle memory. It's real, and it even applies to things like mathematics and learning languages. Actually, the process of writing the language, the symbols, and connecting that process of writing to the act of thinking in time, at the same time, it really can help you start to um, literally change the neurons in your brain so that the pathways where these sorts of concepts the pathways through which these concepts flow start to literally get burned into your brain. Um, it's really fascinating the way the brain works. I say burned, but it's calcium and ion transfer that helps build strong calcium pathways actually in the brain that makes strong pathways that helps us remember things. So anyway, definitely recommend that you try to take a few notes during class too. Other questions? Have you attacked the problems for the proof portfolio?
The measure two is stuff.
Yeah. Darius, you're in the Tuesday, Thursday class, right? Or you
Yeah,
know,
no,
yeah, Monday,
Monday and
Wednesday.
Wednesday.
Yeah, oh yeah. So y'all don't have the proof portfolio in Monday, Wednesday. I'm kind of doing an experiment and having the Tuesday, Thursday class write a proof portfolio. But yeah, the measure two material is like it's non-trivial stuff. You really need to work through these problems because I mean, have you looked at them for chapter 4? It's part of what I'm
Yes,
exploring.
I did the first part. I haven't done the second one yet.
You've done these proofs?
Yeah, just the first part. I haven't done the second one yet.
So do you want to share those with me? You want to take a picture of them and send them to me and let me look at them?
Yeah, sure. I can do that.
You might want to. I mean, I've been sending out announcements and stuff that, hey, you should share your proofs with me and let me look at them. But if it's not for a grade, that's part of what I'm exploring, is whether students are actually taking advantage of materials if they don't have to do it for a definite part of the grade. And I think I'm gonna find out that what I think. But anyway, did you look at all these worksheets before test one? Yes.
Not yet.
Wow. So I'm sorry. I guess I just didn't make it clear enough that there was lots and lots of extra practice to do. Um, and I had all these problems here for you to work on, and they even had solutions, that you could look at. But that was all before test one. I'm not going to post the solutions to these proofs because I don't want them to get. Sure. Yeah, I posted all this stuff, all these worksheets with solutions, like you were supposed to work through these problems, and then I had the solutions there for you, and this was supposed to help you. There's the solutions. This was supposed to help you prepare for test one. I had just lots and lots of them. They all had solution sets, and practice. And it was a practice quiz with solutions. I don't know if you worked through that. But anyway, this measure four material, this chapter four material, I know the first question is just definitions, and of course you have to know those. But all these nice proofs, you should work through them. You need to be able to do these. Okay. Right, we still have another week, and we're gonna have a workshop on proofwriting on Wednesday and Thursday. But we're gonna start some new stuff tomorrow and Tuesday. We're gonna learn another proof method, proof by contradiction and proof by contrapositive. So we're trying to move on from proof by cases to indirect proof methods tomorrow. So other questions? Are there specific questions or proofs that you've been looking at that you need help with, anybody?
I haven't had the time to go through all of that yet.
Well, the thing was, yeah, I get it. I understand. But but I pushed the test back, right? I pushed it back a whole week. And so this is it, right? This is the week. It's time now. All right, folks, it's almost 9:30, and I still need to post these notes and update the YouTube. Hey, listen, there are some good videos, earlier office hour videos, so you can look at those on YouTube, right?
Okay.
Do you know where those are?
Yes.
I think that the address is in the syllabus, but it's also at the top of the reading page. I put my YouTube at, what's it called? Your YouTube address or whatever. Anyway.
Well, the channel.
Yeah, the channel. I have one, but
Isn't it like your name?
oh goodness, come here. Look, let's go back. Let's go back to this let's go back to this great stuff that's like here for you to use.
Yes, since I've already subscribed to that channel, I usually just put your name in the search bar and then your videos will pop up. That's all.
Yeah, but I'll show you another place to find it. If you go to the reading page, the reading page is our one-stop shop that tells you everything. It's right here. YouTube videos. It's up here at the top row. But it's also in and I just actually stopped posting a bunch of stuff. I just finally just said, see the good stuff material because I got tired of just posting lots and lots of stuff. But I try to point people to the measure two material. There's lots of stuff, lots of stuff to do. I should probably just delete this. Well, that's because there's the good stuff folder. There's some other stuff in the good. In fact, there's going to be some new stuff in the good stuff folder. Anyway, but yeah, so here's my YouTube channel. And if you go to the playlists, of course, I can see things you can't see. All right, but if you go to my playlists, and I tried to make a bunch of stuff private. I've made the playlist private, but then the videos are still up. But anyway, spring office hours for
Excuse me,
260.
Professor, we can still see your paper.
Oh, you can't see. Thank you so much. You know how tired I am. You realize that I'm not even sharing. So here's my YouTube channel. So I was just showing stuff that you weren't even seeing on the darn it. All right. Anyway, I apologize. But anyway, of course I can see things you can't see. But discrete math pre-recorded videos, these will actually be helpful this week. Office hours for 263. This one's supposed to be private, but I think there's a bunch of lectures that you can actually see. But I've got my linear algebra stuff up too. I think this is supposed to be private. Yeah, my lectures from fall. But I think that when you have a playlist in YouTube, let me just ask you a question. Like I have this playlist, right? I made the playlist private, but it's got all of these videos in it. Do I have to when this is private, are those videos visible to you? Is that or like separately or is everything in that playlist private? Does anybody know?
So when
Isn't
it's
it the
private,
entire
it's
folder
only
being
you.
private?
The entire folder, the entire playlist, I struck as private. Do I have to go and make every single video private too, or is everything that's in that playlist automatically private?
No, I think the entire folder is supposed to be private as long as the videos are in this folder.
Okay, so these like I've got videos because I taught this online, but because it's got other students, see, for privacy reasons. I mean, we have security training, and there's something about, you know, allowing that to stay up more than one semester. But hey, these office hours are public, and that means anybody could watch them. I suppose I should have y'all sign a form or something to make sure you don't mind, right? I don't know. I don't think anybody's really paying attention. I guess I could provide everybody with a link. I just didn't want to make it that hard. My goal is eventually just to have a freestanding lecture for every single section of the book. Just have with no students involved, and then it can always be public forever. All right, well, are there any other like last minute burning questions? Was there a question that we didn't get to that you really wanted to have me answered? Okay, thank you for coming. Thank you for playing.
Thank you, Professor. Have a good evening.
Nora, thank you.
Bye.
Good night.
Thank you so much.
You're so welcome. I hope to see you again soon. You're doing much better. I'm so glad that you're coming to office hours.
Yeah, I want to do my best, so I'm trying.
Well, I'm here for you when you want to take advantage of it. And the free tutoring center, they've got some people tutoring 263 there too. That they've got some students that are pretty decent. I've recommended some of my students that were good students. So you can go, the free tutoring center, right? In York Road 109.
Yes.
Yeah. So
So
maybe,
when I go there, most times they don't have tutoring for Math 263. I will have to like come back like around 4.
oh, so did they post a schedule on the door that tells when, or are they not actually following that schedule very well?
I don't think they're following it because I do get emails on the tutoring, and most times I don't even see Math 263 among like
Good
the
choices. It's true.
yes.
It's true that they really focus in on like 115 and 117 and 119 and 221 and the calculus, they really work hard to get tutoring for those. It is hard to find good tutors for 263. Um, I think I have the name of a student or two. Didn't you ask me for a private tutor name at the beginning of the semester, Tega? Did you?
Yes, I was just about to ask you about
Yeah,
that.
I wanted that too.
All right.
I don't
So,
mind.
so do email me tonight, and I have the names of two students who would like to earn some cash, and they are good students. I will send your names right to them, okay?
Okay.
Okay.
And you can, and we can have, I know Darius, was it you that asked when we were having office hours tonight? Was it you? No, it was Micah. But we can have an office hour tomorrow night. All you have to do is email me and ask. I mean, if I can't do it, I will say so. But it's like I'm begging people to please email me for help.
Oh,
We can
see,
do it again. We can do it again. We can do it on Monday and Wednesday. We can do it again on Friday.
the thing is, I have a full-time job and I'm also a full-time student. So yes, the timing is not really perfect for me. I only get free time when I'm on campus.
No, it's so hard. It's so hard. Um, I have had really good students, advisees who they had to work full time, so they just said, you know what? I'm gonna take 6 years. It's gonna take me 6 years. I'm only gonna take 2 classes a semester. And he finally graduated and he did really, really well. You did really well, but it
Yeah.
took them a long time because otherwise, what happens? You're taking 4 or 5 classes and then you're failing one or two of them, right? Or not doing well. Then you wind up paying all this money, but you're not getting good grades, right? It's sometimes, but it depends. They will give you financial aid for part-time, right?
Yes. And the thing is, I'm actually doing well in the rest except for math because math requires the constant practice or something like that. So yeah,
I
yeah,
get it.
yeah.
This
I
is
just
like,
Same
want
same with
I
me. Like it's
right?
math that's the issue.
Okay, so email
I
me for the tutor's name and we'll try to get your private tutor. And then you just, work me, just make me earn my pay, and we can try to Zoom more often. I get that you're working. I get that. I don't know what your schedule is. Everybody has a schedule, right? Everybody is working. Sometimes I can do it in the morning though.
okay. Yes, because I just contacted my advisor today and I was asking him if I could drop the class, and he said if I drop it, I won't be able to, graduate on time because I'm planning on graduating next semester.
Have you taken this before?
No, this is my
I'm
first
gonna,
time taking
I'm
this
gonna stop
class.
recording.